Welcome back, LeetCode extraordinaires. Welcome back, practitioners of the hyperbolic coding chamber. I'm back once again. It's June 27. I'm feeling good. The same problems from last time are here. Excel sheet column, fried it. 2 sum 3, we got fried. And we got some other ones set up here. I want to start doing some DP or backtracking problems. So I'm going to check whatever's due today. And then I'm going to try and do some DB problems because I just can't do them. I'm going to keep it a buck. I can't do them. I don't know what I'm doing. Weird camera angle today since I'm looking down, but I'm really looking down at anyone who's not in the Discord. Shout out the Discord. It's jumping. We got 200, maybe 300 people now in the hyperbolic coding chamber. Lots of secret insider tips and tricks on how to ace all of your coding interview, and also general inquiries about the meaning of life and what to do, when you're trying to figure out some problems. So I got 40 minutes on the clock, same setup as usual, and actually need to check something. Okay, I've returned. I had to get the server set up, but doesn't look like we have much. We don't have any cards due today, so never mind. Okay, never mind. We do have a couple of cards due today, so it is what it is. Min stack and merged array. Feel pretty confident about those, but in terms of the top interview questions on LeetCode, I have 44 of 145 done. Most of them are easy problems. And yeah, most of them are easy, actually. Actually, all of them are easy, it looks like, except for one. So now we're actually getting some of the difficult stuff. But I actually wanted to do more DP or backtracking stuff because I wanted to really have a chance for just some certain things. But yeah, and I definitely I've barely touched any hards. So that's probably a problem as well. At the same time, I want to rush the process to do more mediums and hards. When I think about doing that, I don't want to do this challenge anymore. So I think what I can do mentally is just keep going like I'm going. I just do whatever the next problem's on the list while integrating the older problems I've done. So I think that's the goal. It works. It takes longer, but it works. Ideally, in the future, the goal would be to have all legal problems done. I mean, you don't really get anything for doing it, but I think that's a cool goal. It's fun to have something to aim for, and I think it'd be really cool to have that done. Just to finally be done with it, I think. But then I'd be doing problems for the rest of my life. But I'm also cool with that. But there's one more thing I wanted to say. Also, I think actually videos of me just existing here and working through the problems, I feel like are a little bit dull. So in the future, maybe this week, maybe I'll start next week, I'm going to aim to do, I'll start with the intro like I usually do, and then, I might just do a voiceover just about what I've been thinking about the process, maybe how ways I could better it, other things that are on my mind. Very Ivan Jurek type beat. Maybe thoughts about weightlifting, just other stuff outside of coding, but also about coding, cognition, cognitive augmentation, knowledge organization, theories of learning, just random stuff I read in books, ideas. I think it's fun to collaborate and stuff like that, but just throwing around some big SAT words. I don't know what most of them mean. Also, my screen isn't filled up all the way. Let me fix that real quick. You know what? This is pretty ghetto. This is pretty ghetto. I'm just going to accept this is pretty ghetto, but it is what it is. Or maybe I can do fit to screen. And this is kind of what I mean when I say it's pretty dull. So there's a lot of me fiddling with the screen and whatnot. So I'm just going to do fit to screen. It comes out the same way. I'm going to push it over to the side like I did earlier, and we're just going to deal with it. And then hopefully the setup is less scuffed next time. So 40 minutes on the clock. I'm going to do the cards. Might be a little less explanatory today. And then I want to try maybe some LeetCode backtracking or DP problems, because those are probably, I think, also more real worldy. Like caching and making those, like being able to reuse answers, is just a good thing to get in the mindset of thinking about. But I also like the slow grind up, like level up nature of starting from easy problems to medium problems. Because easy problems, they're really simple, right? But you learn like a small trick that is actually very useful for like another problem. So like sometimes I'll do a medium problem and I'm just like, oh, this is just, you know, part of LeetCode 7 plus the end of LeetCode 17 plus, you know, the middle of 222 or something like that. And it's just an easy way to string things together. There's also something to be said about doing something outside of your comfort zone. The human mind and even the human body seems to somehow get stronger when you do things that are outside of your comfort zone or outside of your current level of difficulty. Tangentially related from the book Ultra Learning, you know, when students are tested on their ability to recall just certain, you know, facts from a class or a test, you know, they do better, you know, if they just try to do brute force recall, like just trying to remember it, like not even reviewing, because we tend to have the tendency to review what we already know. We actually do better by just struggling to remember something. And so that's what I'm kind of trying to get at, and just trying to keep things difficult but not too difficult so that I quit, but just difficult enough that I can still manage to log on to this godforsaken website every day. But that's what it is. June 27, maybe day 14, maybe day 15. Either way, it's, you know, another day, another dollop of misery. So I'm just gonna jump into it, and I'm gonna remember to start the timer. And my cam looks good. Also, I look good. Okay, let me stop. But yeah, min stack. Just gonna jump into it. Also, the Intel Mac batteries are not good, so we'll see if we last 40 minutes. Class min stack, we have a constructor. This is what we're not going to need. And we have 4 functions, or it looks like 4 class methods that we need to implement. So design a stack that supports push, pop, top, and retrieving the minimum element in constant time. So this makes sense. Void push, int val pushes the element val into the stack, right? It sounds like standard stack implementation here for pop and top, removes the element on top of the stack. Top gets the element on top of the stack, but doesn't remove it, and get min retrieves the minimum element in the stack. So you can do this with just 2 parallel arrays, and we'll just call the first one min stack, right, which is actually just going to store the minimum value, right? The value so far actually let's do it with stack, and then we're going to have min stack, which actually stores the value of the smallest element we've seen so far. So stack is just a regular stack, which is an array we're going to operate with pop, top, and push, which we get for free in constant time. And min stack is what we're going to use to get min, this class method, in constant time. So there's just a case that we're just going to have to continue to keep handling over and over again. And the first of that case is if the stack is empty, or if min stack is empty. So pop, top, and get min will always be called a non-empty stacks, which means we don't have to worry about making sure that the array isn't empty. But it's just good to mention that. So I'm going to say if stack.length equals 0, right, we have to add this, right? Then we want to do something special. But the real question is, why are we checking if the stack is empty, right? Why can't we just add this .stack.push val? And we can. The problem that changes, right, is the way we get min to be in constant time. We actually have to keep track of the minimum at the time of insertion. And that minimum is always going to be a function of the math.min of the value that we're adding or trying to push onto the stack, and the value that we're trying to push onto the stack and the last perceived minimum in the min stack, right? When we say last perceived minimum, well, min stack is empty, right? And if that's the case, then min stack we actually can't take the end, we can't take a function of math.min at the current value and the last value. So in this case, to illustrate it, what we do is we actually say this dot min stack dot push val, right? Otherwise, if it's not empty, then we actually want to push this dot min stack dot push the math dot min of the value that we're adding onto the array and the last value in the stack. And we should be good there. And we're popping, they said we don't have to worry about pop, top, and get min operating on empty stacks. We're going to implement it anyway. So if this dot stack dot length, right, does not equal 0, right, then we're going to pop this dot stack, duplicate it for this dot min stack as well. For top, right, like we said, we don't have to check this, but we're going to check it anyway, right? If it doesn't equal 0, right, we're just going to return this dot stack sub this dot stack dot length minus 1, just get the top element on the stack and return it. If it doesn't, right, we're just going to return -1. Then for get min, we can do what we've been doing so far, right? So if the stack is empty, or if the stack isn't empty, right, then we know that min stack isn't empty, right, because they're parallel. So when we pop something onto the stack, the regular stack, we actually have to pop it from the min stack as well. And it's confusing because I keep saying min stack, and the class is called min stack. We call it the stack array and the min stack array. But they're parallel, right? So if the stack array is empty, then the min stack array is empty. So if the stack isn't empty, then the min stack array is empty, so we can actually just return this dot min stack, so this dot min stack dot length -1, right? Else we're just going to return -1. We actually don't need this extra else. So I'm feeling pretty confident about this, but I'm going to run it in my head just to be certain real quick. Does it make sense? So we're going to do new min stack. We're going to push -2, so just start stack dot push -2, so we push -2 into the stack, and then the stack isn't empty, right? So we push min stack dot this dot min stack dot push val. Right. So we're actually going to want this to be min stack. So if the min stack is empty, then we just want to push the minimum so far as the value that we're being pushed onto the stack, right? Otherwise, right, we're gonna, do what we said we would do. Now we're gonna push. So in the current value, right, after running this min stack dot push -2, stack equals -2, and min stack equals -2. Now we're gonna push on 0, right? Well, we're gonna say this dot stack dot push val. So we're gonna push 0 onto the stack. And then we're going to check if the min stack is empty. Well, is the min stack empty? It's not. It has -2 in it, right? So then we're going to push onto the min stack the minimum of the value that we're adding, which is 0, or the last element in the min stack, which is -2. The smallest value there is going to be -2. So those first two checks work out, and then we're just going to check for get min. For get min, the stack isn't empty, so we're going to return this dot stack. Oh, no, that's top. That stack isn't empty, so we're going to return this dot min stack dot length -1 for the last element in the array, and return -1. So I'm feeling pretty good about that. So let's run it to make certain. So that looks good, and this is going to run in linear time. Actually, no, constant time. Going to run in constant time for all operations. Push, pop, and top you get in constant time for free, just based off the nature of arrays. And get min is why we keep 2 parallel arrays, right? And so the space that we're actually going to store is going to be linear space. So in this case, we're quite literally creating time complexity or space complexity for time complexity. So that looks good, and then we're going to do merge sorted array. So we have function merge nums1, we have an array of numbers, and then we have m, we have nums2, which is an array of numbers, and then we have n. Do not return anything, modify nums1 in place instead. Interesting. So you're given two integer arrays, nums1 and nums2, sorted in non-decreasing order. If they're sorted in non-decreasing order, that means they're sorted in ascending order. And two integers m and n representing the number of elements in nums1 and nums2 respectively. Makes sense. So nums1 has m elements in it and nums2 has n elements in it. We merge nums1 and nums2 into a single and two integers m and m representing the number of elements in nums1 and nums2 respectively. Merge nums1 and nums2 into a single sorted array in non-decreasing order. The final sorted array should not be returned by the function, but instead be stored inside the array nums1. To accommodate this, nums1 has a length of m plus n, where the first m elements denote the elements that should be merged, and the last n elements are set to 0 and should be ignored. Nums2 has a length of n. We're basically merging two sorted arrays, but the array that we're sorting it into is actually one of the input arrays. So we have m equals 3, which is the number of elements in nums1 that actually store elements, and nums1 has enough as a length of m plus n, so it can sort both elements in both arrays. And nums2 equals 2, 5, 6, which means n equals 3 can store the 3 elements in the array. 1, 2, 3, and 2, 5, 6. Right, until they're being merged right into a sorted array. So I think the most important part, right, is what makes this difficult is that we're merging two arrays into a third array. The third array happens to be one of the input arrays. So the way to make this simpler, right, I think would be to actually convert nums1 into a temp array. So nums1 to a temp array, right? And once we merge nums1 into a temp array, and we can merge temp and nums2 into nums1. And so yeah, that makes the most sense to me, so I'm going to do that. So we're going to do for const let I equals 0, I is less than nums1, right? Actually not nums1.length, we're going to go up to m, right? Because m is where we actually have values as declared by the input. And we'll just do temp.push nums1 sub I. So temp should now store a copy of numbers in nums1 up to m, and now we want to merge temp and nums2 into nums1, right? So how do we go about doing that? So we know that we're going to need to do, right, up to m plus n operations, right? Because n, they said that nums, right, 1 has a length of m plus n, so it always has enough space to store them both. We have to make sure, right, that m plus has enough space for it, but does it always equal it, I think is the real question. Actually, no, yeah. So we're actually good. Nums1 always has enough elements to store both m plus n, and if that's the case, m and n always equal number of elements within nums1 and nums2, so we're good. That means we're always going to do m plus n operations, right? Because we have to merge them. So if we want to merge them in sorted fashion, right? We each have two arrays, right? Let's say we have 1 in, in this array, and 6 in this array. We would just check, right, the most recent value or the last value we haven't touched. In this case, neither of them would be index 0, and we'll just take the smallest one, right? And then 1 would go into nums1, replacing whatever value is there. So we know that we need to check, right? We're going to need 2 pointers to keep track of the last elements we copied into from temp in nums2. So we'll just call this p1 equals 0 and p2. Don't have any bindings set up, so I'm just going to do that real quick. Also, let me check. Text might be a little small. Make it a bit bigger. So if p1 and p2 equals 0, right? And what we want to make sure, right, is that p1 is less than p2. Oh, no. If p1 is less than m, right, it means we haven't copied all the elements out of nums1, right, out of temp into nums1. And so that means when we index the array with this pointer, it'll actually exist. So if p1 is less than m and nums1 sub p1, right, is less than, not nums1 sub p1, if temp sub p1 is less than nums2 sub p2, right, then it would be the smallest value of the two. So you would say nums1 sub I, and our third point is actually going to be I, right, because we're going to fill this nums1 up with m plus n values, going to get the value of temp sub p1, and we're going to do p1 plus equals 1. You probably guessed the else case, it's going to be the opposite, right? If temp sub p1, right, p1 points at 1 here and p2 points at 6, if 1 is not less than 6, right, well, this is a bad example. Let's just say it's 12 and 6. Well, if 12 isn't less than 6, then 6 must be less than 12, right? So nums1 sub I will get the value of temp sub p2, and we'll do p2 plus equals 1, and then I feel pretty good about this. There's actually going to be one case, right, one more case, right? So this else clause is a really good job of catching another case, right, that is actually we actually don't see, right? So imagine this: we have 6 and 2 in nums2, and nums1 we have 12, right? So if we have 12 and 6 and 2, right, if we do p1 is less than m, well, p1 equals 0, and it is less than 1, right, which would be the number of elements in nums1. We have 6 and 2, right? So is 12 less than 6? It's not, right? So we're in this else case, right? And we're going to copy, right? Let's just set nums1 equal sub 0 equal to 12, right? So far, right? But now what we notice, right, is that when we do p1 is less than m, well, 1 isn't less than 1 anymore. So we automatically shuffle the remaining elements in nums2 into nums1 because of this else clause. So -1 becomes, 6, and then, -1 here becomes 2. So this else clause does a great job of shuffling, right? When p1 is out of elements, it shuffles all the remaining elements from p2 into nums1. We need to also make that process symmetrical by adding the same functionality for p2. So when p2 is empty, right, when we process all the elements, right, from p2, and we can duplicate this again, right, we're going to say we have 3 -1s, right, we're going to say, hey, is p1 less than m, right, well, p1 is 0, right, and is 8 less than 6? No, so we shove 6, right, into nums1, right, and we do p2 plus equals 1. Well, then we go to the next iteration, right, we're going to say, hey, is p1 less than m? It is, right, 0 is less than 2, but is temp sub p1, right, which is 8 less than nums2 sub p2? Well, nums2 sub p2 is index 1, and index 1 doesn't exist. Well, is 8 less than null, right? And that doesn't make any sense, right? So we need something to mimic that that overflowing or that shimmying property, right? So else handles if p1 gets emptied, we'll shovel all the remaining elements into p2. We need another case or condition in this first loop to make sure that the extra elements, right, when p2 runs out of elements, all the remaining elements in temp get shoved into nums, right? So we're going to say, or if p2, right, is greater than or equal to n, right? Then we want to shift all those remaining elements into all the remaining elements from temp into nums1. So I'm just going to wrap this in parentheses just because it's a little easier to read this way. And I feel pretty confident about this one, but I'm just going to run it. I think we already ran it by talking through it, but I'm just going to run it. Okay, that was to be expected. That's why you always run it. Always run through it one last time. So it looks like the expected output is 1, 2, 2, 3, 5, 6. And we're outputting is 1, 1, 2, 3, 2, 3. So if P2 is greater than or equal to N, which means maybe I shouldn't do equal. Oh my God, no, you wouldn't want to do equal. No, wait. So let's just say P2 equals 1, and there's only one element in it. We're going to say that to 1, and then we're going to say, or P2, then we want to shove it in. Well, yeah, I think you actually do want equals. You shove the remaining elements from temp sub P1 into num sub I. Well, let's run it with the input to see what's happening. So we have 1, 2, 3. So nums 1 equals 1, 2, 3, 0, 0, 0. And then duplicate that, right? And temp is just going to equal like this. Duplicate that, we're going to make nums 2, which is equal to 2, 5, and 6. And we're going to have 3 and 3 for both m and n. So m, n equals 3. Right, so it looks like everything works up until the 4th iteration, so we can just skip to there. So 0, 1, 2, 3, 4. So you get to the 4th iteration, I equals 4. I is still less than 6, so P1 at this point would equal, yeah, I guess I'll just start from the beginning because it's confusing. So P1 equals 0, P2 equals 0. Is P1 less than M? So P1 is less than M. M would be 3. Is temp sub P1 less than nums 2 sub P2? Well, 1 is less than 2, so yeah, nums 1 sub I equals temp P1, so that is it's equal to 1, right? And P1, right, would now be equal to 1. P2 would still be equal to 0. And then we go to the next iteration. Well, I equals 1 now. Is P1 less than M? Well, P1, which is 1, is still less than still less than 3. And temp sub P1, which is 1, is less than num sub P2. So is 2 less than 2? It's not. So we would just shove, temp sub P2 into num sub I. And then P2 would be equal to 1. And then 1 is still less than 3. Is 2 less than 5? It is less than 5. It is less than 5, so we would sub temp sub P1, which is 1, into num sub I, so it would be 2 . Oh my god. Oh, I just figured out what the problem is. I'm copying the numbers from temp in both cases into nums1, where it should be nums2 sub p2. Oh man, that's why when it's always a learning process. Doing this now, I'm realizing I fill in a lot of blanks in my head. I'm not actually reading the code. When I double check what's wrong with code, I need to actually go line by line, no matter how mind-numbing it is. To see the details. So it looks like my first implementation was right besides. Oh, I forgot. Yeah, I took away my equal sign because I was editing. This is what I meant. It had to be equal. So there we go. This is going to run with a time complexity of m plus n with a space complexity of m or n, depending on which array you want to hold in the temporary memory section. In this case, I chose nums1, so we know we have m elements in it, so it's going to be a space complexity of m. So that looks fine. And I wanted to clean up a problem from earlier, and I did say I would try some deep here backtracking problems. So, let's try add two numbers. But I'll finish up two-sum data structure design first. I think I know actually how to do it now. So basically, we have to design a data structure that can solve the two-sum problem. And the two-sum problem is that given an array of numbers, we want to be able to check if it has a pair of integers that sum up to a particular value. Now you can do this in n squared time just by checking all possible combinations, but that's a bit slow. One other thing we can check, right, is that there's a solution to this that is a two-pointer approach where it looks very binary search-like, but it's pretty interesting in the method by which it finds the low versus the high. And so one way that we could do this is that the prerequisite for that original implementation with two pointers actually requires that this data be already sorted. And so we actually need some properties ahead of time, like is sorted and r, which would just set to an array, which will restore the values that they're asking us to add. So when they add a value, right, we're just going to say r dot push number, and we're going to set is sorted equals to false. So if we added a new number to the array is no longer sorted, right? It's not really a self-sorting data structure. But when we want to find the number, right, we're going to check. It's like, hey, if this is not sorted, right, then what do we want to do? Well, we want to sort it in place, right? And we'll just do a function version or callback version of sort for this JavaScript function, right? We can kind of add our own comparator. So this is going to sort it in ascending order, right? And then we'll set this dot is sorted, which is true. So what we'll be able to see is that this is optimized for loading a large subset of numbers in. And then if you call find successively, right, it's optimized for that because we only sort it, right? We'll only resort it once you add a number again. So this is optimized for a find heavy use case. And so the way you would go about implementing this, I think we'd have a low, right, which equals 0, right? And we're trying to find two numbers such that when they're added together would equal value, right? And our left and our right, we're just going to make it look a lot like a binary search. But it's not, because we're really just going to be subtracting by 1. It's going to be like a linear time solution, basically. We're going to let right equal to r.length minus 1, the last element in the array, right? And so this is going to run right while left is less than right, right? So this, I think the lack of the equal sign makes sure that you need at least two distinct indices to make this make sense. And so what we're going to do is we're going to say, hey, if the number at left plus the number at index right, and we'll just shorthand this to value, or sum, if sum, right, which is num sub left plus num sub right, right? So if sum equals value, right, then that means we have on our first iteration found two numbers when added together that equal the number that we're looking for, this find function, right? Which is perfect because then we can just return true. The other thing, right, is very binary search, like where we have two range in which we're checking in. The reason it's not a binary search is that we're not having the search space on every iteration. So it's just linear time. So if the sum, right, is greater than the value that we're searching for, then we actually want to slide down our right margin just a little bit. And if our sum is less than our value, oh no, I actually got it in reverse. If our sum is greater than the value, right, then we're more likely to find the correct sum if we inch our left margin up, right, because it's sorted in ascending order. So what I mean by that is if we took this array 1, 3, and 5, left would be 0, right, and right would be the last element in the array. So 2, right, as indices, right? And so if we say, let's just say try and find 4 like they mentioned here. So add, fine, we try to find 4, right? We're gonna start with 1 and 5, right? Left is less than right, 0 is less than 2. There's num sub left, which is 0, plus num sub right, which is 2. There's 1 plus 5 equal 4. It does not, right? So we're gonna go to the next thing. Is our sum of these two numbers, which is 6, is 6 greater than 4? Well, it is. So if we're at the largest part of the array, if we imagine this sorted, which would be 5, if we subtract from the larger side and move forward one forward right, we would technically still no, actually I think it is fine the way it is. The other way doesn't work. So yeah, right, this just illustrates how it works. 6 is greater than 4, right? So we would slide our right margin down, so we would actually go to index 1. And we'd go to our next iteration and check the sum of the values where 1 and 3 would actually equal the value we're looking for. Otherwise, on the next iteration after that, both indices would be the same, 3, and we would end, right? So we'll just default to false outside of the loop. But if sum is less than the value, we're actually more likely to reach it if we increment our left margin by 1. And so I actually feel pretty confident about this one, but maybe that's a recipe for it failing. So do this .r.sort, and we also have one on line 16 and 18. I call it nums, but it should be this .r. Cannot find name. Num, that was 18. So let's see what this looks like. So that is pretty cool. That should be a linear time solution for find, but in the worst case it would be n log n. But average case, linear time if we're optimizing for a find heavy use case. And then I'll try a add two numbers type beat. So definition for a singly linked list in JavaScript, we have a class which is a list node, it has a value, and it has a next pointer. So this is a singly linked list, meaning it only has one pointer pointing to the next node. Constructor simplifies creation of this linked list. And then we have function add two numbers, which has one node and another node which returns a node. Interesting. We're given two non-empty linked lists representing two non-negative integers. digits are stored in reverse order, and each of their nodes contain a single digit. Add the two numbers and return the sum as a linked list. Okay. So the numbers are stored in reverse order. So 243 means -342. And so they want us to do -342 plus -465. Oh, I'm not reading close enough. Linked lists representing two non-negative integers. So they actually want us to do 342 plus 465 equals 807 and return it as a linked list. Interesting. So they're both non-empty. The sum for that one is 0. So I kind of want to just split the problem in 2 points. One would be the summing part, and another function would take a number or string and convert it to a linked list. And maybe if we could figure that out, we could fuse those functions into one, or maybe optimize it some way. That being the case, I think the first thing that matters is that you need to be able to iterate over a linked list in reverse. And we could do that with 2 stacks, but I think there's an in-place version that would use no memory. But the list would be destroyed, I believe. So maybe we could make a function called reverse. You know what, let's make it work first. Let's make it right. Then we'll make it work. No, let's make it work. Then let's make it right, and then we'll try and make it fast. So the summing part I'm going to do with the one I know how to do it easily, and I'm just going to call it I'm just going to do it with a stack. So we'll just reverse it twice, and we can actually make this a function called reverse, and it's going to take L1, which is a list node, or null, and return a number. And then what we'll do is we'll just call this function twice. We'll call the first one num1, and we're just going to call reverse L1. And we'll duplicate it, we'll get num2, and we're going to call reverse L2, right? If L1 equals null, right, we're going to return 0, right? And if it's not, right, then we're going to use a stack, right, to basically get the value of the number in reverse. And so we'd use a stack, which we're just going to use technically an array, and just only operate at the end of it. And we're going to do a standard loop through a linked list. So let cur equals L1, while cur does not equal null, right? We're going to operate, right? We're going to do we're going to do stack dot push cur dot val, right? And do cur equals cur dot next. At the end of this, right, we should have our stack, right, filled with the numbers but in reverse. If that's the case, then we'll just iterate over the stack in reverse order. It's going to be, we're going to start at I equals the stack dot length minus 1, which is the last element. While I is greater than or equal to 0, we're going to do I minus minus, and then we're going to have the string, right? So this one is like a string-based version, and then we're just going to do string dot push because we have to recreate the string basically. And we're going to do string plus equal stack sub I. And then we can return the parse int of string, which would be it in reverse. And then we can take the sum of both of these numbers, which would be num1 plus num2. And if we can take the sum of both of these numbers, then we just need a function that turns basically a list of numbers into an linked list. So we can create, actually we can just do it here, we'll just call it LL, right? We're just going to call it new tree node. It's not going to have a value, and we're going to do for const, and we're going to actually have another one called temp. We're going to set it equal to ll, and we're going to say for const. Actually, it's actually fine if we keep it as a. Oh, no, we need it for yeah. So we'll actually do for const car of sum.toString. So now we're going to take the number to a string, and we're going to say temp.val equals car. Parse int car, and then we're going to do temp.next equals new tree node. And then we can return ll. Feel good about this one. There's only 45 seconds left, so if it was an interview, you would just really just click run code. Next does not exist on tree node. Oh, it's list node. Oops. Oh man, 708. I have the number, it's just not going all the way to the end for some reason. Oh, and at the end we could do it one last time. No! Oh. So it's really just about inserting that last element. And I think the way to do it, you could literally just go if temp does not equal null, and you just set temp.val equal to actually might have been easier to do it with a 0. I is less than sum.toString length I plus plus, and you can just say the string of I, but we want, oh, this is so ghetto, I equals 0 out here, and then you would just say I there. Yeah, this definitely could be optimized to not be this ghetto. So now it's just non. We sum.toString, right? And then we're subscripting it with the value that we're currently at. Actually, there's, you know, we can keep it the original way and then just do I equals 1, and the first list node that we create, you know, we'll just check, right? If right, if some string dot length, right, equals, oh, it's literally just off by 1 error. Temp.val equals parse int car, temp.next equals new list node. I think the best way to keep it simple is just for this to be a while loop. Just change this so let I equals 0, I plus plus down here, and I'll set up this key binding real quick, and it will just run while I is less than some not toString dot length. You want to be inclusive of the end. Oops. Main car. Oh man, I'm trash without an IDE. You can just actually do some dot car at and just do I, and you'll get a character. And type number. Oh my god, it's not even a number. I mean, it's not even a string. I'm so confused. Car at I. I'm just gonna print car. Yeah, 807. Eight, 0, 7. And you're supposed to add the two numbers and return the sum as a linked list. Should the linked list should also be in reverse. Oh, I see. Even so, I'm off by 1. Oh no, wait, my output. I think I can test it right here. I'm gonna put 1 into the link, into the node. Doesn't matter, I forgot because it gets reinstated. There's one last thing I want to try. Cars equal sum dot toString, then I'll spread it into an array, and I'll go while cars dot length is greater than or equal to 0. Car is going to be cars dot length minus 1 thrown into parse int. Then in the past, temp.i equals parse int, temp node. Go to new list node. There'll be no more I nonsense. It's gonna run forever because I'm not doing cars.pop. My endurance is trash. Shouldn't be taking this long. I don't understand why I'm getting so many nons. If I'm popping it off of the end of car, is pop not? I thought pop operated on the array. Cars.pop. Oh, it can't be log greater than or equal to 0, otherwise it never ends. So let's just wait. Maybe this, yeah, I got confused with, I used equal sign. Now this is giving me 807. But they want the output in reverse as well. The problem is I'm not even getting the last element in the array. If the last element, if we get the last, if cars.length equals 0, then I'm just gonna end up doing a ghetto version of the loop. While n is greater than 0. If length equals 0, oh, my brain is fried. I'm just trolling now. Length minus equal 1. I know how to get, I don't understand why the last element is not existing. Length equals 0, and we're just going to do 10 dot val equals car sub. I'm literally writing spaghetti code now. Greater than or equal to 0 when minus equal 1. if length it's off by one error is so nutty. I'm iterating through this number I've got, which is 807, and I just need to have the output in reverse, which I can already do by iterating over the array in reverse. Once you get there, all you need to do is assemble a linked list from it. What I need to do is start the list node. Just go back to what I had originally. I is equal to sum.toStrength.length minus 1. I is greater than or equal to 0. I minus minus. Num is equal to sum.toString car at I. So we're actually going to start it at -2, and then I'm going to remove this cars.pop nonsense, all of these special cases, length nonsense, and cars nonsense. Still going to print the sum, except when I create the list node, it's going to get the value of .toString sub 0, and I'll do a safe navigation on that, or null. Or what does it set it to? Or 0. And then LL will actually start at LL.next. Comma expected. Sum.toString car at I, saying a comment was expected at car 54. Cannot set properties of null setting val. Temp.val equals num. Oops, I'm passing in the last number here. Should be an even longer version. Again, -1. I think this should be it. So I'm returning 780. 807. The number I have is 807, and sum dot to the last sum dot length minus 1. $708. Let me just do -2. First. The last element, this should be correct then, 780, but it's in the wrong order. Temp.val. I'm literally guessing. I'm literally guessing at this point. I just have to return to this one tomorrow. I'm literally just guessing. It's awful. I should run the code in my head to figure out what the problem is. I'm just guessing. RIP.